So for the next few chapters, we're going to focus on small kind of chapters in your book that don't have a number. Instead, they use letters, and these are going to focus on spectroscopy. And we're going to look at spectroscopy in sections A, B, and C in your textbook. And the first one we're going to talk about is mass spectrometry. And I want you to look at the molecule here. This is nucletone, and I'll spell it. And it's a really fragrant lipid that's a key component in the aroma of grapefruit. Now, research from the CDC shows that it acts as a repellent for ticks, mosquitoes, and other insects, and works better than other natural insecticides like citronella. So one of the things that we do as chemists is we determine the structure of organic compounds when they are isolated from natural products, like the grapefruit here. The other thing that we do is we synthesize compounds in the laboratory, and we need to figure out their chemical structures as well. So to determine the structure of organic compounds, chemists use a variety of instrumental methods, and we're going to look at those as we go through chapters A, B, and C. And so we're going to start with mass spectrometry, and mass spectrometry is just a method that's used to determine the molecular weight and molecular formula of compounds. Now, it can do quite a bit, and I'm sure that you'll have other courses that are dedicated to mass spectrometry later in your educational career. And so this is really just meant to be an introduction to mass spectrometry. So let's look at a kind of cartoon of a mass spectrometer, okay? In a mass spectrometer, right, we have a sample that is injected, and that molecule is vaporized. So if it's in a liquid form, it's turned to a vapor, and then it's ionized by bombardment with beams of high energy electrons. So we have an electron beam here, and it's traveling at a high energy, something along the lines of 70 electrovolts. And what it does is that electron beam ionizes the molecules, and it causes it to eject an electron. Now, that will then travel through the tube where we reach a magnet, and that magnet will separate out those different components, and that's where we get different peaks that show up here on the mass spectrometer. Now, these are deflected by different amounts depending on their mass to charge ratio. So let's look at we're going to put some of this into words on the next slide, okay? So when the electron beam ionizes the molecule, the species that's formed is called the radical cation and is symbolized with an M+. So we inject the molecule into the spectrometer, it gets bombarded with a beam of electrons, and what happens is one of those electrons of the molecule is broken off, and now we have a radical cation here. So when the electron beam ionizes the molecule, the species that's formed is called a radical cation, right? And it is symbolized as M+, and a lot of times you're going to see like a dot there, okay? Now, that radical cation, the M+ with a dot, is often called the molecular ion or the parent ion. Okay, so we've got a lot of different synonyms for that. And now what this tells us about the compound is that represents the molecular weight of the compound. So this is a really nice way for us to determine the molecular weight of an unknown compound. Now, because that M plus is unstable, it's going to decompose to form fragments of radicals and cations that have a lower molecular weight than M plus. And those fragments can tell us some information about the structure of the unknown organic compound. Now, I want to remind you that radicals have an unpaired electron. So as we're talking through radicals, that's what we're talking about with those unpaired electrons. So the mass spectrometer analyzes the mass of the cations. Okay? And what you're going to see here is that the mass spectrum is a plot of the amount of each cation, which is its relative abundance, versus its mass to charge, which is M over Z is what we talk about there, where M is mass and Z is charge, right? Mass to charge ratio, okay? So since Z is almost always +1, the mass to charge ratio generally measures the mass of the individual ions. Okay, so let's look at an example of a mass spectrum when we get it. So when we look at a mass spectra, what we're going to see is that we have the relative abundance here on the y-axis, and then we have the mass to charge ratio here on the x-axis. When we look at this, the tallest peak is called the base peak. So the base peak is the tallest peak. And then we also will notice we have a molecular ion peak. Which can also be called the parent peak or the M peak, right? And that is going to be the peak that gives us the molecular weight of the compound. So right now we're looking at methane, which is just CH4, and what we're going to see here is the molecular ion peak, where we have a mass to charge of 16, is also the base peak. Okay, so these two can be the same or they can be different. Now, the molecular ion peak, I want you to notice, right, when we calculate the molecular weight of CH4, right, that's approximately 16 grams per mole. And so we can see here that molecular ion peak shows up at 16. And that's where we see the molecular weight of the compound. Now, I want you to notice something else. We have an M+1 peak. Okay, And mass spectrometers can distinguish between isotopes. And so we have an M+1 peak because approximately 1.1% of carbon atoms have a mass of 13. So what we're seeing here is just that some CH4 molecules will have a mass of 17 instead of 16 because there's the isotope carbon-13. And so since we're looking at mostly carbon compounds, almost all the spectra that we look at are going to have a M+1 peak, which again is due to carbon-13. Now, let's look at why we get some of those other fragments, okay? Because we see the base peak here, we see the molecular ion peak, we see an M+1 peak, but we also have these other fragments too, and so I want to talk about those just briefly. So, the molecular ion is unstable, okay? This is a really unstable ion, and what it will do is it will fragment into other cations and radical cations containing 1, 2, or 3 or 4 fewer hydrogen atoms than methane. And so from this, that's where you get those mass peaks of 15, 14, 13, and 12. And so that's why we see the other fragments in the mass spectrometer, is because we see that this just removes a hydrogen atom each time. So let's look then at a little bit more complicated spectra, which is hexane. So we're going to come over here and we're going to look at hexane, and a few things to identify kind of out of the gate. The first one is we have the molecular ion peak here, and that's 86. And that corresponds to the molecular weight of hexane, which is C6H14. We also can identify the M+1 peak, which is 87. Now, what we're going to see here is the base peak is not the same as the molecular ion peak. It's right here at 57, right? And then we also see major fragment peaks that occur at 43 and 29. And so I want us to look at kind of those differences really quickly. So we have our molecular ion peak of 86, which indicates a hexane, right? And then we have our base peak of 57, and this is our next big peak. So if we take 86 and we subtract 57, right, we get 29, okay? And so what this means, when you look at this molecule, is that it has broken right here to form a cation. And so this corresponds to that 29 molecular weight that's lost, or that's broken off, right? It's not really lost, it's just broken. Okay, and then the 57 that you're detecting here is this molecule. And so it's CH3, CH2, 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 and a positive. Okay, and that's cation, that's why we can detect it. Then, right, if we look at the next base peak, sorry, the next peak, not the base peak, but the peak after the base peak, right, and we're still analyzing this molecule, what we find when we take 86, which is the molecular weight, and subtract 43, which is what we've lost between 86 and here, 43, that's what's broken off, right? So we can say, hey, look, this molecule is going to break off right here because that leaves 43, right? So what we are detecting then is this part of the molecule there, right? And then if we look at the very last peak there, and we take 86 and we subtract 29, which is the base peak that we see, not the base peak, which is the peak that we see here, right, past the base peak. So we take 86 and subtract 29. What we're showing here is that this is the part that's broken off, and so that equals 57, which is the mass there. And then 29 is what we have left, and so we are then detecting this part here. And when we detect that part, we are seeing CH3, CH2, that cation. So we can get information of fragmentation patterns from mass spec as well. So I want us to do an example. Okay. The spectra for pent-1-ene and pent-1-ine are shown below. Match the spectra with the molecule. Now, we haven't talked about these structures yet. Pent-1-ene, this ene here indicates there's an alkene, right? So that means we've got a double bond. And then the YNE indicates that we have an alkyne, which is a triple bond. We're going to get to this in the next couple chapters. If you run into something like this, or it's asked on a exam, I'm going to give you those structures of anything that we haven't talked about that's not an alkane. So what I would do is I would also show you these structures as well. So I would come down here and I would say, okay, hey, look, we've got pent-1-ine, right? And pent-1-ene, and I would give you the structures. I would say, hey, look. Okay, this has a triple bond here. We've got 1, 2, 3, 4, 5 carbons. And then here, 1, 2. We also have 5 carbons, 1, 2, 3, 4, 5. And of course you would recognize the pent, we've already talked about that. So you would have to go through and figure out the number of carbons and hydrogens. We have 5 carbons here and 8 hydrogens. And then over here at pent-1-ine, we've got 5 carbons here and 10 hydrogens. So there's a difference of just 2 hydrogens. So the next part is we would calculate the molecular weight. And so we see that the molecular weight here is 68 grams per mole. It's approximate. There's some decimals there, but we're really working with whole numbers here. And then this is about 70 grams per mole. So we would expect the mass charge ratio for pent-1-ine to be 68 for the molecular ion peak. And that's what we see with this spectra. So we can match pent-1-ine to this spectra. And then pent-1-ene, we would expect that molecular ion peak to be approximately 70, right? And so this spectra has a molecular ion peak of 70. And so we can match this molecule to this spectra. And so that's an example of how we would use mass spectra to identify an unknown. Now, let's talk, maybe the burning question in your heart is, Dr. Pierce, we have looked at things with just carbon and hydrogen. What happens when you throw in oxygen and nitrogen and halogens? And I'm so glad you asked that. So let's talk about nitrogen first. Now, hydrocarbons, as well as compounds that contain only carbon, hydrogen, and oxygen atoms, are always going to have a molecular ion with an even mass. So, hydrocarbons and compounds with just carbon, hydrogen, and oxygen always have a molecular ion with an even mass. Now, an odd molecular ion generally indicates that a compound contains nitrogen. Okay, this effect is called the nitrogen rule, right? And so all it says is that a compound with an odd molecular ion contains an odd number of nitrogen atoms. Okay, so if you've got an odd molecular ion, you generally have an odd number of nitrogen atoms. Now, the unfortunate thing is if you have an even number of nitrogen atoms, that's going to give an even molecular ion. So let's look at an example. These are two street drugs. One is 3-methylphenol. And what we see here is it's got 2 nitrogen atoms, so it ends up with an even molecular weight. But if you look over here, this is MPPP, and it just has 1 nitrogen atom, and it has an odd molecular weight. And so that's where we can see that nitrogen rule, where you would have an odd molecular weight here and then even molecular weight there. So let's do an example where we have to propose possible molecular formulas for a compound with a molecular ion with a mass to charge of 154. Okay, with an even mass of a molecular ion, the compound likely contains carbon, hydrogen, and possibly oxygen atoms. And so for right this second, we're just going to ignore nitrogen, mostly because it's a very small molecular weight. As well as, this question isn't asking us to propose all possible molecular formulas. It's just asking us to propose a few possible molecular formulas. So the first thing that I do is I'm going to assume this guy either has carbon and hydrogen or carbon, hydrogen, and oxygen. Okay, those are my two assumptions because it's an even number. And so I am going to figure out kind of the max number of carbon atoms this guy can have. So I am going to take 154, which is the molar mass, and divide by 12, that's the molar mass of carbon, and that gives me 12 carbons with a remainder of 10. Now, that remainder of 10, we can assume is hydrogen. So a formula could be C12H10. Okay, that is one possible formula. Now, when we get into questions in your book, it's going to be a little more specific. It's going to say propose a molecular formula, which is like one molecular formula. Some of them will say propose 2 molecular formulas. So that's a little different than what we see here. Now, my next step to determine other possible molecular formulas is to replace one of the carbons by 12 hydrogens. So my next step here is I'm going to replace one carbon by 12 hydrogens. Now, when I go through and I do this, that means now I'm going to have 11 carbons, and then 10 plus 12 would give me 22 hydrogens. And so I need to ask myself, does this make sense? Okay. And the way I do this is a few different ways. And so one of the things I do is I think back to alkanes. And when we learned about alkanes have the structure, right? CnH2n plus 2, okay? And so for 11 carbons, that would be H2 times 11 plus 2. And that would be C11 and then H24. We also learned that cyclic compounds have the generic formula CnH2n. When we look at this, right, we say, okay, there's C11H2 times 11, which means this is C11H22. So what we find is that this is the max number of hydrogens that a molecule with 11 carbons can have, okay? If we have over this, that means it's not possible, right? Because this is the max. Now, what we're going to see here is we have 2 fewer hydrogens than the max. So this indicates that this is possible for this molecule, and it could be a ring, okay? The difference here with those 2 hydrogens is called the degree of unsaturation. And what we are talking about here is that every pi bond or ring in a molecule removes 2 hydrogen atoms from the molecule, introducing 1 degree of unsaturation. So what we find is that the C11H22 does make sense. A few other things to help you evaluate if these make sense. Alkenes are going to have the same general formula, CnH2n, where they've also lost 2 hydrogens for every 1 double bond. And so that would also, if it had 1 double bond, it'd be C11H22. And then alkynes, which have a triple bond, are going to be CnH2n minus 2. And so this formula would end up being H20, okay? And so all this to say is we want to make sure that we don't have over the maximum amount of hydrogens, which we don't have here. When we come up and evaluate this for C12H10, this makes sense because what we can do is we can say, hey, look, we've got C12H12 times 2 plus 2, that's C12H26, okay? And so 26 minus 10, right? So we have 26 hydrogens minus 10 hydrogens in this formula gives us 16. And so that's 16 hydrogens missing. And so that means this molecule could have 8, right, double bonds, right? Or it can be cyclic and have, 3 double bonds and a couple triple bonds, right? So we look and use this information to figure out, do these make sense? And so this does make sense because it's lower than 24, okay? So let's do all of that one more time. Now, let's look at kind of another example. So let's take off 1 more hydrogen. So I'm going to kind of come over here and take off 1 more hydrogen. one more carbon. So that would be C10, and then I need to convert one carbon into 12 hydrogen. So it would be C10H34. So we need to check, does this make sense? So we come here, CnH2n plus 2. So if it's C10, then it's going to be H2 times 10 plus 2. And that comes out to C10H22. So this guy here is not possible. Okay, so that's not a possible option. It doesn't make sense because this is the max number of hydrogens when you have 10 carbons. Okay, now let's then come down and talk oxygens for just a second. To determine the max possible oxygen atoms, you replace CH4, right, which has a mass of 16, with an oxygen. So we started with, right, that got really dark, C12H10. And then what we need to do is we need to replace, right, one carbon and 4 hydrogens to add that oxygen. So we subtract CH4, and that gives us C11H6O. Now, when we talk about the degree of unsaturation, and oxygen, you need to just use, for the double check, give the given number of carbons and hydrogens and ignore oxygen, right? So we just ignore oxygen when it comes to this. So for the double check, we would say, look, the max number of hydrogens that we can have for this molecule is still C11H11 times 2 plus 2, which is H24. So this formula makes sense. We're not over on our hydrogens, which is what we're worried about. We can then check and see if we have another oxygen atom. When we have C11, H22, right? So here we can subtract 1 CH4, and that would give us C10H18. And so we would say, okay, does that still make sense? C10H2 times 20 plus 2, C10H, 2 times 10, right? 22. Okay. And so it's still less, so that would make sense. Okay. And then from here out, we would subtract, we could go so far as to subtract another CH4, right? So that would be another formula, and then we could subtract another one if we wanted. And that would be C9H14O2. Okay, and then a quick double check tells us those hydrogens are going to be under the max as well, so that's a possible formula. So these are all different possible formulas for that mass to charge ratio of 154. We've got some practice problems, and of course we will work on this in class as well. If you have any questions, please feel free to stop by my office.